Hey everybody, it's Ripper back again. I'm about to give you the keys of the kingdom. I'm going to give you the most important integration skill that there is. Very much akin to what chain rule was. Whoops. What chain rule, awesome. What chain rule was to derivatives. Integration by substitution is to integrals. Okay? Now, if you recall, over here, we have a list of integrals. There's what, 14 on this list, depending on your textbook, depending on with whom you're working. There could be more or there could be less. The problem is, what if I'm taking integrals of functions that aren't on this list? Then I'm boxed in. Then I'm stuck. So, for example, let's look, wait, let me look at that list again. Like, look at what we got. We got the integral of sine, cos, secant, and we don't even have, secant x, tangent x. We don't even know how to take antiderivatives yet of tangent, secant, anything like that, which is kind of a bummer. So what mathematicians started doing was, okay, how are we going to figure this out? Well, we need something that undoes chain rule, that makes chain rule go away. For example, if I want to take the integral, let's just do, wow, that just keeps doing that, doesn't it? If I want to take, and it's going to keep doing it to me. Oh, come on. Huh. Okay. I'm sorry, you guys. This is, I don't know what's going on there. It hated me for just a minute. Oh, I might edit that out, or I might not. Let's get rid of this. Okay. So for example, if I want to take the integral of something as simple as sine of 5x dx. All right, it's an indefinite integral. Take the integral of sine of 5x. The problem is, it's not part of the list. Look, it's not on the list. I don't see sine of 5x. All I see is sine of x. So how am I going to do this? Now, there's a really tricky part of integration by substitution. And the hard part is that we have, right in the middle of our integral, we're going to need to take a derivative. And that's going to feel weird. But I'll show you why that is in just a sec. Now, the rule of integration by substitution is very simple. It simply says you can integrate, or you can substitute anything that you want into your integrand. Anything you want, as long as you account for everything. For example, hopefully you notice that 5x is what I refer to as the trouble. And this is one of the techniques, of the two major techniques with integration by substitution, is find the trouble. Find the thing that's making your integrand look, or excuse me, not look like the integral on your table of integrals. In this case, it happens to be 5x. I'm going to let u equal 5x. Now the reason, I want you to know this method to my madness here. The reason I'm doing this is because if we sort of look at this parenthetically, if I had the integral of sine of u du, well, that's just equal to negative cos u plus c, right? So my objective is to try and make this guy look like this guy. All right, let me go back to my black pen here. All right. U equals 5x. So think of this not as just u, but kind of u as a function of x. If I take the derivative of this, I could write it as u prime of x equals 5 if I wanted to. But I'm going to write it in Leibniz notation. And the reason I'm going to write it in Leibniz notation, as we've seen before, is because Leibniz notation is awesome because it's algebraically separable. All right? Now here we go. Right? du over dx is equal to 5. There's a problem, though. I have accounted for the 5x here, but I want to account for this dx as well. Remember, I can substitute whatever I want into an integral as long as I account for all the parts. So I can rewrite this as du equals 5 dx. That's why Leibniz notation is so helpful, because I can algebraically separate that derivative. Now, I don't want a 5 dx. I want a dx. So I get dx is equal to du fifths. Now, I'm going to rewrite this integral after I've done this substitution and watch what happens. Now, that 1/5 is a constant, and that's the coolest part, is I can pull that constant out in front. Remember, the integral of a constant times a function is just the constant times the integral of the function, so I throw it out in front. Now I'm going to count for all my parts. Well, 5x, that's this guy, was u, so this becomes sine of u, and then dx is equal to du fifths. I pulled the fifth out in front, and I'm just left with a du. If I wanted to, I could stick the 1/5 under here, but that would be like, what does that mean? Sine u equals du fifths? We'd want to pull it out anyway. So here, now look at this. We are where we need to be. This becomes 1/5 cosine of u. Oh, careful. Let's throw our negative out in front, right? And then plus c. Now, if you don't believe yourself, take the derivative. Oh, wait, except this is in terms of u. Wait, this function was in terms of x. However, will I get back? Well, u is just equal to 5x. So I can rewrite this as negative 1/5 cosine of 5x. I'll put it in parentheses because I wrote it so poorly, plus c. Now I'm done. Let's do another one. Let's do a common one. How about the integral of 3x minus 9 to the 10th dx? Now, one of the challenges of integrating by substitution or being new at it is kind of seeing where the trouble lies and kind of knowing what you know and knowing what you don't know. If I look at this, it should be relatively obvious that if this were, again, parenthetically, let's put this guy over here, parenthetically speaking, if this were the integral of u to the 10th du, this would be really easy to evaluate, right? This would just be u to the 11th over 11 plus c. Yay, smiley face. It'd be easy, but I don't have that. So what do? I integrate out the trouble. I'm going to let u equal 3x minus 9 du over dx. This is the last time that I'm going to do that because it just adds an additional step where I can do something silly. Du over, by this I mean write this full Leibniz derivative out. All right, I'm going to skip straight from this step to that step. Okay, so this becomes 3. So du is equal to 3 dx. Again, I don't need 3 dx. I need a dx. I've accounted for the 3x minus 9. Now I need to account for the dx. So dx is equal to du thirds. Now I'm done. So that implies that this integral becomes 1/3 the integral of u to the 10th, I don't know why I'm talking that way, of u to the 10th du. And I have transformed this integral into this integral. And poof, watch what happens. This just becomes 1/3 u to the 11th over 11 plus c. We'll clean it up in the next step. Here it comes. Well, what was u? U is 3x minus 9, right? What's 3 times 11? 33. So this just becomes 3x minus 9 to the 11 divided by 33. And this is plus c. And so when I take the derivative of this, watch what happens. I get 11 times 3x minus 9 to the 10th times 3, right? If I use chain rule, and those 33's cancel, and I'm done. The derivative of the constant goes to 0. You can always double check what you're doing, right? You can always double check your integral by taking a derivative. All right, now that's a trouble part, and I'm actually going to give you a couple of tricks and a couple of hints to get you through that. It'll make your life easier down the road. But let's deal with a different kind. How about the integral of 1 over the natural log of x times x, I'll put the x in front, dx. Now in this case, this integral this could also be written, you'll see these in textbooks, sometimes written as dx over x, ln x. In this case, it doesn't look anything like one of these guys that we want to memorize, right? And there's no trouble per se. It's the natural log of x and it's x. So this is, we'll call this type 2. And this is look for a derivative of another part of the integrand in the integral. So check this out. I've got 2 parts of this function. Now, they both live in the denominator, which can get a little bit confusing. One is the natural log of x, and one is x, but it's not really x, is it? It's 1 over x. Ding! And my brain just went, aha, because I've memorized all of my important derivatives. Excuse me. I might see that u is equal to the natural log of x. Remember, I can let u be whatever I want. For example, let me do it in red. I can let u equal 1 over x. Now I'm gonna do these sort of parallel. If I let u, let's do the wrong substitution first. If I let u equal 1 over x, then du, notice I'm not going to write du over dx anymore, is going to equal negative 1 over x squared dx. Now look what I would have to do. If I want to account for everything, this 1 over x would account for this part right here, but then I would have to account for dx. dx would equal negative x squared du. Wait, what? This is already confusing. And then I still haven't accounted for the natural log of x. The purpose of u-substitution is to funnel. Think of it like a funnel. You're funneling a difficult integrand into an easy one, into one of the ones that we memorized. That's where I want to get. So this bad math. If it gets more complicated after you've done your u-substitution, chances are you've done the integral wrong. So du equals natural log of x, or excuse me, u equals natural log of x. Du is going to equal 1 over x dx. Now look what happened. We accounted for the natural log of x, and then this guy right here is accounted for in this part. So I can completely rewrite my new integral as the integral of, guess what? 1 over u du. You'll often see this written as du over u. We know this is the natural log of the absolute value of u plus c. This is equal to, I need to back substitute, right? Because I started with a function of x, and now I have a function of u. So this becomes the natural log of, wait, what was u again? Well, that's weird. Natural log of the natural log of x plus c. And I'm done. Let me do another one. You ready? Because these can get a little bit tricky. Let's do the integral of e to the root x over root x dx. Now this one's tricky because you're probably looking at it immediately and you're like, okay, I'm either gonna let u equal root x, or I have to let u equal 1 over root x, right? So it's my question mark. Which one of these do I want to do? Well, hopefully you see that if I take the derivative of 1 over root x, it's going to get more complicated, and it's going to be really tricky to account for this root x that is the exponent of e to the. So let's start, and there's absolutely nothing wrong with backing the train up and starting over. Let's start with u equals root x. If I let u equal root x, then du equals 1 over 2 root x dx. Remember, I'm no longer going to write this as du over dx equals this because I just end up here anyway, and I don't want to insult your intelligence. Okay, so that root x right here, this guy right here, has accounted for that guy right there. I'm really, really close, aren't I? I need a dx over root x, and I've got one here, so what do? Well, I just multiply both sides by 2, and I get 2 du equals dx over root x. And now I can integrate this guy, can't I? Because dx over root x was 2 du, so I'm going to pull the constant out in front. I'm going to get the integral of e to the u du. This 2 du is accounted for here. This e to the u is accounted for here, right? Which is awesome. And now look how simple this thing is. That's the beauty is they distill down into much simpler forms. So this becomes 2 e to the u plus c, which is 2 e to the root x plus c, and I'm done. That's it. Man, that's pretty straightforward, isn't it? Now, that said, these can get pretty awful. These can get super awful if you're not careful. They can get pretty tricky pretty quickly. But for example, let me do this one. This one isn't even bad. Let's go 6x minus 2 over 3x squared minus 2x plus 19 pi dx. All right? On the face of it, god awful, horrific, right? But if you don't panic, if you're looking at it, you're like, okay, this isn't one of these guys where I'm just kind of looking for trouble, right? Because it doesn't look immediately like one of my fantastic, in this case, 14. However, if I look close, look, the top is a perfect derivative of the bottom. So now I just go, okay, I'm going to let u equal 6x minus 2. Whoops, try that again. I'm going to let u equal 3x squared minus 2x, 3x squared minus 2x. Now, do I keep the 19 pi in there? The question, or the answer is, of course I do. I want to take all I can. I want to take every little bit that I can, especially in this derivative, because when I find du, I end up with 6x minus 2, and then there's my little dx hanging off the end. So notice, had I not done that, if I just grabbed the 3x squared minus 2x and ignored the 19 pi, then I would have had to account for that 19 pi later, either with another u-substitution or just by seeing it, which is no fun. Look at that. That is exactly what I want. I want a 6x minus 2 dx. So this integral becomes, the top is just du, the bottom is u, and guess what? We end up with the natural log of the absolute value of u. Don't forget your absolute values. In my class, you forget the absolute values, you get popped for a point. Also, if you forget your c, you get popped for a point. I can rewrite this as the natural log of the absolute value of 3x squared minus 2x plus 19 pi and absolute value plus c. And we're done. That's kind of cool, huh? Now, I've got a couple of, I want to use this a couple of ways. I need to take a break really quickly. I'll meet you back here in just one. All right, sorry about that. Need a little break, fix my head. Well, it's going to take more than a little break to do that, but we all know that. All right, anyway, so what I do want to show you is that integration by substitution gives us the ability to solve for a few of our integrals. We can actually fill in all the blanks on our trigs. I'll show you. For example, if I want to take the integral of tangent of x dx, all right? We're going to do the general antiderivative for tangent of x. Well, we're stuck here. There's nothing I can work with, right? Because I know the derivative of tangent of x is secant squared, but there's no secant squared laying around. However, I do know that the integral of tangent x is sine x over cosine of x dx. Now, I have two choices at this point. I can either let u equal sine of x, or I can let du equal either 1 over cos x or just du, or I can let u equal cosine of x, or even 1 over cosine of x. Now think about that. If I let u equal sine of x, then du is going to equal cosine of x. And you're like, oh, that's clean, Ripley, but it really isn't, because now my du is in the denominator. What does that mean? Now I'm dividing through by the width of the subinterval, which gets you back to, wait, that doesn't make any sense, right? So this would have a dx on it, by the way. So let's start with u equals cos x, because then du is equal to sine x dx, which is exactly what I want. It's perfect, all right, which is great. So now remember, if push meets shove, we can always back up the train. I can rewrite the integral as the integral of du over u, which is equal to the natural log of the absolute value of u plus c, which is equal to the natural log, oh, whoa, easy Ripley, sorry, I got to simmer down here. I forgot a negative, didn't I? Right? So this would become negative du is equal to sine x dx. Slow your roll, Ripley. Goodness gracious. So I'm going to put a negative here, and I'm going to put a negative here, and this becomes, now I'm going to have to do a little erasing, give myself some space. This becomes the negative natural log of the absolute value of whatever u was, which is cosine of x, plus c. It's kind of it's not a really intuitive antiderivative. It's like, how did we get from a trig to a natural log? Now, if you remember your laws of logarithms, I can actually raise the whole thing up to the -1, and cosine of x raised to the -1 is 1 over cos, which is secant. So you'll sometimes see this written as the natural log of the absolute value of secant x plus c, right? Just you understand how, hopefully you understand how that happens, because cos of x raised to the -1, not inverse cos of x, but cosine of x raised to the -1 is 1 over cos, which is secant. And there you go. Okay, now similarly, if I want to take the integral of cotan of x, this one actually gets a lot simpler. This, I would let u, this equals the integral of cosine of x over sine of x dx. So now if I let u equal sine of x, excuse me, then, excuse me, then du equals cos of x dx. Goodness, which is exactly what I want. So now this becomes the integral of du over u, notice no negative this time, which is the natural log of the absolute value of u plus c, which is equal to the natural log of the absolute value of sine of x plus c. We're done. Now do it. Okay, so hey, we got tangent cotan knocked out. How about the integral of secant x dx? Oh, good gracious golly. That's going to give me some fits because we're in the same boat, and the only way to rewrite this is the integral of dx over cos x. What? So now if I let u equal cos, I'm going to have a negative sign, or if I let u equal 1 over cos, which is secant, then du is secant x tangent x. There's nowhere to go here. So what I'm going to do is I'm going to multiply by the goofiest looking one you've ever seen. And you're going to be like, what are you doing, Ripley? Let me erase this really quickly. I'm going to multiply. Remember, I can always multiply by 1. No, don't do that. I can always multiply by 1 whenever I want, as long as I'm not dividing by 0, right? Now, this 1 is going to seem really counterintuitive, and it's very clever that they figured out that this works. I'm actually going to multiply, not by sign, I'm actually going to multiply by the secant of x plus the tangent of x plus the tangent of x over the secant of x plus the tangent of x. Whoops, that's supposed to be parentheses, right? That's just a goofy looking 1. This turns into the integral of secant squared x plus secant x tangent x. I'll put the dx over here. Your spidey sense might be tingling a little bit already because you see why? Secant squared x, whoa, that's the derivative of something. Secant x tangent x, whoa, that's the derivative of something. What is that derivative of? Oh, it's the derivative of secant x and tangent x. Put a plus right there. So now watch how easy this is. Go back to my black. I'm going to let u equal secant x plus tangent x. Du is equal to secant squared x plus, well, I should probably do it the order in which they're done. The derivative of secant x is secant x tangent x plus the derivative of tangent x is secant squared x. And there's my dx. And that is exactly what you want. So this turns into the integral of du over u, which is the natural log of the absolute value of u, plus c, which is equal to the natural log of the absolute value of secant x plus tangent of x plus c. And guess what? You're done. All right, now there's one more little tricky one, and then, I won't walk you through the full pace because this video is starting to get a little bit long, but if you look at cosecant x, well, maybe I will. It doesn't take very long. If I multiply through by cosecant x plus cotan x over cosecant x plus cotan x, that's just a goofy looking 1. And what we end up with is, I'm going to have to give myself some space over here. Maybe I'll just kick over to the next page. This thing turns in to the integral of cosecant squared x plus cotan x cosecant x. Again, your spidey sense is probably tingling a little bit. And I get cosecant x plus cotan x. Let's move this guy up here, right? And if you look close, u is going to be the denominator. Now the numerator is very close to the derivatives of cosecant x and cotan, except what do we know? Well, if it's got a co in front of it and I take a derivative, I get a negative. So if I let u equal cosecant x plus cotan x, then du is going to equal negative cosecant x cotan x minus cosecant squared x dx. Now I just factored the negative out and send it over. So negative du is equal to cosecant x cotan x plus cosecant squared x. And I have exactly what I want. That's this top guy right here. So this becomes the integral of, oh, don't forget your negative, Ripley. Respect thy negative of what? Du over u, which is negative natural log of absolute u plus c. And this guy turns into negative the natural log of the absolute value of cosecant x plus cotan x plus c. And guess what? Super smiley face, because we have all 6 trigs accounted for. We now officially know all 6 antiderivatives of the trig. We couldn't have done so without integration by substitution. Now there's one other tricky one that can get you into trouble. I want to show you. Let's say that I have x plus 1 over the square root of x dx. Now you got to be really careful because you can learn these new tools and then you're going to think that you're like, oh man, integration by substitution is awesome. What a big hammer I have. Now I'm going to use this big hammer to hit everything with. Well, the problem with that is, excuse me, hit everything with a big hammer, you can do a lot of damage to the little nails, right? And you don't always have to. So recall, all of your other skills are fully in place, like, shall I say, algebra. I can totally rewrite this integral because this is a common denominator. I can rewrite this integral as, what can I rewrite it as? The square root of x plus 1 over root x dx. Now, no integration by substitution is required. Square root of x is x to the 1/2, so that turns into 2/3 x to the 3/2. I just did the x to the n plus 1 over n plus 1 plus c thingy, right? The antiderivative of 1 over root x, I've memorized this. It's not a bad idea for you to memorize this as well, but it's 2 root x because x to the negative 1/2, if I take x to the negative 1/2, doesn't this guy turn into x to the positive 1/2 divided by 1/2, which is 2 root x, and then plus c. Now I'm going to do one that's not quite as pretty. It's innocuous enough looking, but it can really give you fits if you're not careful. What if I do the integral of x over x plus 1 dx? All right? Now you're like, okay, that doesn't, wait a sec, it doesn't have any square roots in it, but I don't have a common numerator. There's no such thing. I can't rewrite this as x over x plus x over 1, right? That doesn't work. However, what we're going to do is, I'm going to do a trick. I'm going to do, let's do our let u equal the trouble. And in this case, the trouble is x plus 1, because it's in the denominator, right? There's nothing algebraic I can do to this to make it simple right now. I reckon I could do long divide this in, but that would be awful. Let's see if we can make it simpler quicker. I'm going to let u equal x plus 1 because I don't like the denominator. Then du is going to be dx. Ooh, that's nice. That's pretty easy, right? Because that's just going to be a du. The question is, how do I account for this x? Well, you guys, I just used algebra. X is equal to u minus 1. Now look at what happens. This becomes, well, we're just going to account for everything, right? X is u minus 1, so this is the integral of u minus 1, divided by x plus 1, which is now u. Oh, and look at how pretty that becomes. And then, of course, dx is du, so I'll just slap that down. Now I'm right back in this position. I can rewrite this guy as, I'll rewrite it down here, as the integral of 1 minus 1 over u du. Hey! That's easy. This thing's a piece of cake. This is u minus the natural log of the absolute value of u plus c. And then we back substitute because I started with a function of x. So this is u is x plus 1 minus the natural log of the absolute value of x plus 1 plus c. And guess what? I'm done. Yay! Smiley face. Okay, cool. Now, one last thing. Well, two last things, technically. I want you to notice something. If I take the integral of f of mx plus b dx, okay? Now what I'm saying is, remember, integration by substitution is running the chain rule backwards. So one way that we use it is to be able to deal with compositions of functions. Now what I'm about to say deals exclusively with linear compositions. In other words, I used mx plus b on purpose. Okay, so I want to make sure that you understand that you can only do what I'm about to tell you if the thing that you're substituting is linear, like in this case, right? All right, so here's what we do. I would let u equal mx plus b because it's the trouble. I know that du is going to be m dx. I don't want an m dx, I want a dx. I just need to account for that. So du divided by m is equal to dx. So when I rewrite this, remember m is just a slope, so it's a constant. I can pull the 1 over m out, and this becomes the integral of f of u du, which I know this turns into 1 over m times the antiderivative of f plus c, which turns into 1 over m times the antiderivative of mx plus b plus c. Now, you may be going, Ripley, what the heck? Why did you just show me that? Here's why. And this is in my class. You might have an instructor that wouldn't let you do this, but at least you'll know whether or not you're getting the correct answer. If I take the integral of, say, the sine, let's do cos this time, it'll be easier, of, let's say, the cosine of 4x minus 9 dx. Well, now I don't have to, what I'm saying is, for my class, you don't need permission, or you have permission to not use a u-substitution on this. You can simply look at it, see that this is linear, know that you're going to end up with a 1/4 or 1 over m. The antiderivative of cos is sine, so this is going to be sine of the linear term, which is 4x minus 9, plus c, and you're done. Likewise, how about the integral of the square root of 3x plus 5? dx. Well, doing a u-substitution on this, you don't have to, because the u-substitution that you would use is u equals 3x plus 5, and u d equals blah, blah, blah. Excuse me. I'm telling you, you don't have to do that. We know that the antiderivative of u to the 1/2, which is the square root of u, is 2/3 u, which is 3x plus 5, to the 3/2. You've taken the antiderivative of the square root a bunch, and this is going to be times 1/3. This 1/3 is the 1 over m. I'm getting that here. Plus c, of course, and this becomes 2/9 times 3x plus 5 to the 3/2 plus c. It saves you time. You can choose to use it, or you can choose not to use it, okay? However, it's not bad when you do use it. All right. So hopefully that gets you squared away as far as using u-substitution. Now I want to do one more thing. I want to do it with definite integrals. Okay, so this is going to be u-subs on definite integrals. Definite integrals. And then we're done. I know this is a long one, but this is the beefiest, most important skill that you learn in all of integral calculus, I promise you. So now let's take the integral. Let's make it fun. Let's go from 3. No, let's not make it from 3. Let's do from 9 to 16 of tangent of root x over root x dx. Okay? Now, here we go. Same problem. We've seen this sort of thing before, right? Yeah, root x is, yeah, screw it. Let's use it. All right, so I'm going to let u, just like I did before, I'm going to let u equal the square root of x, and I know that du is equal to 1 over 2 root x dx. This is the same sort of thing that I did with e to the root x. I just wanted you to see a little different one. I don't want 1 over 2 root x dx. I want dx over root x, because I can take the integral of the tangent of u. So this becomes 2 du equals dx over root x, and I'm loving it. Now, the question is, what do we do with these limits? Now, I can do it two ways. I can either treat it just like I did the antiderivatives with indefinite integrals with the plus c, and then evaluate it after I've back substituted. So I can do the back substitution, which I've talked about, right, to get you back to x, or I can save a ton of time. And the way I save a ton of time is, look, I just created a relationship between u and x. These limits were on x. So why don't I build a bridge from u to x, right? I know when x is 9, since u is root x, u of 9 is going to be root 9, which is 3. I know that when x is 16, I'm going to take u of 16, which is root 16, which is 4. And guess what? We just turned this guy into the integral from 3 to 4 of tangent of u du. Now the cool part about this is once I have changed the limits, these two are exactly equal. There is no difference between the integral from 9 to 16 and of this guy and the integral from 3 to 4 of this guy. So I can actually forget about this integrand that had limits on x. I have converted everything over into u's, so there's no back substitution necessary. So we just learned, that this becomes the natural log of the absolute value of secant of x I'm not going to put my plus c because it's a definite integral. And I can simply go from 3 to 4. And this is equal to the natural log of the absolute value of secant of 4 minus the natural log of the absolute value of secant of 3. And I have no idea what those are, right? But we can plug them in our calculator. And we're going to assume that they're radians because we want real valued functions of a real variable. Okay? That's pretty cool. This is just a number. Now you may say, wait, Ripley, where'd the c's go? Remember, if I've got a definite integral, I don't need the c's because the c's cancel. Right? I could do this plus c, and then when you subtract out using the fundamental theorem of calculus part 2, those c's disappear. Let's do one more. Let's do the integral from, let's go, oh goodness, let's go from 0 to pi halves of cosine of x divided by the square root of 1 plus sine of x dx. Okay? I don't know why I just stuck that where I did. That's crazy. All right, again, what do you think? What do you think I should let u be? Well, I know that cosine is the derivative of sine, but again, like I said before, let's grab all we can. I also know that cosine of x is the derivative of 1 plus sine of x. So now I'm snatching the 1 as well. So I've got 1 plus sine of x. I know that du is equal to cosine of x dx, right? I also know that u of 1, let's try again. I also know that u of 0, deep breath Ripley, that u of 0 is equal to 1 plus sine of 0, which is just 1. I also know that u of pi halves is 1 plus sine of pi halves. Well, sine of pi halves is 1, so 1 plus 1 is 2. Guess what? Once we did that, I can completely abandon this integrand in terms of x. I can simply say that the new integral is the integral from 1 to 2 of, now let's double check everything, cosine of x dx, that's just du, over the square root of 1 plus sine x, that's just the square root of u. And this becomes 2 root u from 1 to 2, which is 2 root 2 minus 2 root 1, or 2 root 2 minus 2. And I'm done. We love definite integrals when we have to do u-substitutions because we don't have to back substitute. We simply change the limits of integration and we're done. All right, everybody. I hope that was helpful. I know it's a long video. I apologize that it's so long, but again, the material that we're doing is so important. Okay? All right. We'll see you in the next lesson.